All right. So this is like take 4, okay? All right, so trying to figure out how to make this whole thing work. So here's what we've got, is that we've got a AA battery and a very strong neodymium magnet on the bottom of that. And then we've got a loop of copper wire that's connecting from the positive terminal of the battery, and then it's actually touching the base of the magnet. So what's that allowing that to happen is that's allowing a current to flow around that wire. So this is a situation where you have the right-hand rule. So you have a current like going down the loop. You have a magnetic field that's being generated from the magnet, and that's creating a torque or a force to make this thing spin. So this is a situation where you have to have both components. You have to have a current, okay? If you look at that, force equals QVB. So you've got a current, you've got charged particles moving, you have an external magnetic field, and that external magnetic field then is creating a torque on the loop, which is allowing that thing to spin. So this is just a kind of a cool way to show that interaction between charged particles and a current and how it can create a force which can make something spin. Okay, so let me stop this because otherwise the battery gets overheated. It's warm right now because of that internal resistance. Okay, now I've got to shift this over here. Okay. There we go. I'll walk around on this side this time. So, here's what we've got. Now, this is what's called a solenoid. And what this is that it's a tube with a whole bunch of wires, of copper wire wrapped around it. And so this is hooked up to a power source. When I turn it on, this thing is going to have a current flowing through it. Now, I've got it set on DC, so that current is only flowing in one direction. But what's happening is that, and again, this is just the simple right-hand rule. So the current is flowing, let's say, around the tube in that direction. So what's happening is that that's creating a magnetic field inside of this tube. Okay, so this is going to be important. Inside of here, we've got a pretty strong magnetic field. So what I have here is these are just very, very fine iron filings. This is actually off of an old VHS tape. And if I take this magnet, okay, that same neodymium magnet, is that I can drag this stuff along, okay, and actually even pull it up here to the top. Yes, at this point, all of you would want to play with it, and I would be more than willing to let you play with this because it's just kind of cool, because you can do kind of weird things with it. Woo! Okay, all right. Now, to show that there's a magnetic field inside this coil, what I'm going to do is I'm going to turn it on, okay, and kind of crank up the current. And so then, when I put this in here, more, okay, what you'll see is that those iron filings are being pulled towards the inside of that loop. Now, if I put it on the outside of the coil, you don't get anything. Okay, it's a very, very weak magnetic field. But on the inside of it, it's a very, very strong magnetic field. So the other way that you can kind of demonstrate this is I've got just your basic metal rod. And again, if I turn off the electricity and there's no current, okay, hey, not a big deal. It just sits there, boom. But if I turn this up, okay, and then let go of it, then, and you can feel this thing, I can actually drag this thing along because there's such a strong magnetic field inside of it. So if I hold this like this, okay, and then let go of it, it actually pulls that in. And even to the point that it's strong enough, let me crank it up, that it will, oh, hold on. So that magnetic field is strong enough to hold that, I'm not touching it, okay? Now, if I decrease the current and lower that down, then eventually the rod falls. So what you could do is say, okay, well, hey, I know how much gravitational force is pulling down on the rod, and then if I know what that is, and then if I can figure out how much force it is provided by the magnet, I can set those two things equal and then get an idea of the strength of that magnetic field inside of that solenoid. Okay? So this is like on doorbells, this is how doorbells work. Like when you ring the doorbell, this will like pull a piece of metal in, and then it'll hit the doorbell and it'll make it ring. So a little bit of application there. So inside the solenoids, you can have very, very strong magnetic fields. So if you've ever been like in an MRI machine, that's kind of how that process works. Okay, so now let me shift the focus back to the big screen. Okay. I'm going to try and get this where we're not crooked. Okay, there we go. Sorry for the technical difficulties, but I got to do this all myself. Okay, so kind of going to go over some random things. So this is the equation we came up with for forces on parallel wires. And again, this isn't on your equation sheet. I will give this to you on the test if you need it. But here's what's going to happen here. And then again, this is just a quick review. So this is the opposite of what you've always been taught. You've always been taught that likes repel and opposites attract. Well, it's the reverse of this when you have wires. When you have wires, if they're going in the same direction, so if they're the same, they actually attract. If they're in opposite directions, where if I have one current going up and the other one going down, those are actually going to repel each other. So when you have two wires, it's the opposite of what you're used to thinking of it. Likes attract, unlikes repel, and that's like different than magnets or anything else like that. So sometimes, and this isn't a huge algebra problem, but sometimes it might ask for force per unit of length. So this is mu naught I1, I2 over 2 pi r, which is just basically the circumference of the circle. So if you want force per unit of length, just take your force, divide it by your L, you get newtons per meter, force per unit of length. There you go. So don't flip out over that. Okay. Now, speaking of loops and how things can spin. So let's say that I've got, and there's a couple of things that are going to be important about this. So number one, this is a situation where you would have a loop. Okay, it could be a circle, it could be a square. I made it square so that it's easier to see. But it's going to be the same no matter what. And so you're going to have a loop that would have a current going through it. And by the current, I mean the traditional sense of the current. And then you're also going to have an external magnetic field. And what we want to do is figure out which direction this loop is going to spin, like I did with like the magnet and the battery. So here's the setup. And I got to view this how you guys are seeing this. So here's this loop like this. Okay, so here's my loop. The external magnetic field is coming from left to right. So the external magnetic field is in this positive x direction. So this is what we got. This is where this thing is going, positive x direction. The current is going around this thing in this direction. So the current is going to be going this way. So what we want to figure out is which direction this thing is going to spin. So here's the deal. This part of the wire, where the current is going this way, is parallel with the magnetic field. So this part of the loop here won't feel anything, nor will this side over here. So these two sides here won't feel anything because they're parallel with the magnetic field. The sign is 0 degrees, there's no force. However, when you get here, so with this one, again, it's this right-hand rule. So the magnetic field is going in this direction, okay? So the current is going in this direction. So I'm going to point my thumb, so here's my loop. I've got the current going like this, okay? So that's going to go in this direction. The magnetic field is going in this direction, and then my fingers are going to point down. So the magnetic field is going to try and force this side of the wire down. So this side over here is going to get pulled downward, okay? So I'm here, the current's going this, the magnetic field is going this, that's going to tend to pull that down. Now, over here, on this side of the wire, so here the magnetic field, or the current, excuse me, is going in this direction, okay? So the magnetic field is going in this direction. Now, this is tough to do. So the magnetic field, the current is going this way, the magnetic field is going this way, so my fingers are pointing up. So this side over here is being lifted up. So if you're looking at the loop, then it would tend to spin clockwise, because this side of the current, okay, this side over here is being pulled down, okay? This side over here is being lifted up. So what would happen is that this wire would spin like this, which is what I was able to pull off with the magnet and the copper wire, which is what allowed that thing to spin. Now, obviously, if you reverse it, then it would spin in the opposite direction. So this thing would spin, if you really wanted to get technical, you would say it's going to spin clockwise. Oh, I screwed that up. Clockwise around the y-axis, okay? So, now if the magnetic field was going like into the page, then you could do the same thing, depending upon which direction the current. So if the magnetic, let's say the current is going this way, the magnetic field is going in, then that would force it this side down, and then it would spin about that x-axis. So then it would go like this. If the magnetic field was going into the page, then it would make it spin about that axis. But here's the deal. Any magnetic field can only act on two sides, because of the fact that you're always going to have sides that are going to be parallel with that magnetic field. So you can only deal with the currents that are at right angles to that, and that's what's going to make this thing spin. Okay. All right. Now, the Hall effect. So this is one of the most important ideas that came out of this whole idea of electromagnetic theory, and whether it's negative charges that are moving or positive charges that are moving. So let me kind of set the stage. You've got a battery here. Here's the positive terminal of the battery. So that's that bigger side. There's the positive terminal. So we're going to go with electrons for now. Okay, we're going to go with electrons for now. Okay? And this is like a conducting metal plate. Okay, so this would be like a piece of steel or something like that, where that current would be going across like this, and then this part of the plate is subjected to a magnetic field that's going into the page. Okay? So, in one situation, the electrons are going like this. Okay? You have an external magnetic field that's going into the page, and then the current comes around like this. Now, the other side of it is, it's the exact same setup, but this one, we're going to go with the traditional Ben Franklin definition, And we're going to have the positive charges coming around like this, and then it's going to hit a magnetic field. Don't worry about the arrows for now. Hold on. Let me make the arrows go away so you're not distracted. I'll put the arrows back in just a second. So you have positive charges going this way into an external magnetic field, and then they're going to come around like this. So what we're going to look at is what's going to happen to the electric field that we're going to see inside of here. So let's start with this one because I already have those arrows there you already seen. So if you look at what's going to happen, if they're positive charges going across, so you put your thumb in this direction because that's the direction the positive charges would go. The external field is pointing into the page. Your finger is going to point down. So what would happen is that you would tend to drive these positive charges down towards the bottom of that conducting plate. Okay? So imagine that like remote control is the plate. So the positive charges are coming in, the magnetic field is going into the page, and you would establish positive charges down here. Now, that's going to create an electric field. So if you have positive charges down here, that means you could look at the direction of the electric field. So with this one, the direction of the field, if you put a positive test charge up here, that positive test charge would, and you'd have negative charges up here because you'd have a deficiency. So the direction of the electric field would actually be pointing upward because a positive test charge in this electric field would be repulsed by the bottom and it would move up towards the top. So if this is what's happening, if it's actually positive charges that are moving down, your electric field would be pointing upward. Okay? If that's what was actually happening. Now, let's assume that they're electrons. Okay, now I'm just going to use the left-hand rule because that's going to be easy. So if I have electrons coming up like this, and then the magnetic field is pointing inward, so I'm going to use the left-hand rule. So I've got electrons coming in like this, the magnetic field is going into the page, and electrons then are going to be forced downward. Okay? So on this one, we're going to take electrons and we're going to force them down towards the bottom of the page, or the bottom of that conducting plate, which would make the top of the conducting plate be positive. Okay? So if this is the situation, if it's actually electrons that are moving, then the electric field would be pointing. So if I put a positive test charge, the positive test charge would be driven down away from the positive and toward the negative, and the electric field would be pointing downward. And this is actually what happens. This is what we actually see. It's because the electrons are coming in like this. We can measure the direction of the electric field in this conducting plate, and we would see that the bottom of the plate is negatively charged. The bottom of the plate tends to become positively charged because we've shifted those negatively charged particles down here. So this is kind of one of the big defining moments in terms of being able to explain, wow, this is what's actually taking place. Is it electrons that are moving, or is it protons that are moving? Or is it the positive charges? And so this is kind of one of the defining things in terms of what we're actually able to see. Okay, so that's the video. I'm going to send out the assignment with the answer key to it. It's nothing out of the book. It's all kind of random questions that I've developed. But I'm going to send that answer key with that. And anyway, stay safe, and that's the story, kids.